So in the morning we talked about very low level stuff, hardware security and how to use this for securing operating systems and applications. And now I'm going to go all the way to the sort of top of the stack and talk about usability aspects of especially about mobile security. So I think like many security people, my training is in protocols and sort of system stuff, and I sort of arrived at this usability by necessity, because I was in particular because I was working for Nokia, which was making devices that are used by ordinary users, and you have to sort of think about usability implication security. So the normal conventional wisdom about usability and security is that they are somehow contradictory, that you cannot have usability and security at the same time. If you try to make a system that is easier to use, then necessarily it has to be less secure. On the other hand, if you try to make something more secure, it has to hurt somehow. And this is even in among the security research community, I think this sentiment was maybe the prevalent sentiment maybe a decade ago. So if I had gone to a decent security conference 15 years ago and want to talk about usability, I wouldn't have been taken seriously. But this has started to change. So in the last, I mean, you saw Stephen talking about this, that usability is a mainstream concern. Everybody realizes that this is important, and without that you might actually compromise security. And there are many good conferences. The top conferences get papers about usability, and there are dedicated conferences. There are PhD theses and so on. So what I'm going to talk about in this lecture is try to motivate why should we care about usability of security, and ultimately, if you have a system that is not that's supposed to provide some security but that's not usable, in the end it will harm security, right? So Stephen talked about passwords and password change policies. So if you have a insane administrator who sets up an insane password security change policy, people find ways of compromising or working around that, right? So they derive strategies for finding new passwords that pass these rules but might actually be insecure, or they write down the password and keep it on a piece of paper. But I think his talk sort of set this up very nicely. So you can enforce unusable mechanisms, unusable policies if you have a captive audience, like if you are the government or if you are an employer. But if you are a business that is competing with other businesses, then lack of usability might actually compromise the attractiveness of whatever you are selling. But in the end, I think the reason why at least the industry worries about usability is it's going to cost money if your security system doesn't have sufficient usability. And at least for me, in some of the cases that I'm going to talk about, the source of this cost was surprising. It wasn't sort of, at least in the beginning it wasn't, in hindsight it was obvious, but in the beginning it wasn't obvious that this is going to be the cost if you didn't engineer usability in. So in these examples, I'll try to tell about the sources of cost. So the way I'm going to do this is I'm going to talk about two case studies, about two specific problem areas where there is this need to balance usability and security. The first one is called Secure First Connect, and I'll tell my experience. So this is actually my first exposure to the importance of usability was in this context of Secure First Connect, which happened about 6-7 years ago. And the second one is more closer to the kinds of things that we have been talking about. So the specific problem of how do you grant permissions to mobile applications. And then I'll try to motivate you why doing usable security is particularly hard in the case of mobile devices as opposed to other kind of form factors. And then I'll end with a couple of other problems which still are crying out for security solutions that balance usability and mobility. So first I'll start with the Secure First Connect. So by Secure First Connect, This is not an official name, but it was a name that some people involved in this work used. First connect is the process of setting up the first connection between two devices. So imagine that you buy a Bluetooth headset and you have a Bluetooth phone, and you want to do something so that your headset will find the phone and your phone will find the headset from then on, so that you don't have to do this every time. And doing so essentially you're setting up the parameters necessary for subsequent communication. And part of that might be actually security. So you want the communication between your headset and your phone to be encrypted and integrity protected, so that other people don't find out what you are talking on the phone or what you're being told. And this first connect situation happens in many places. So this Bluetooth accessory and phone is one. Every time you go to a new place, you have to enroll your device to the local wireless network. That's a first connect problem as well. So any situation where you have to connect two devices or maybe more devices together so that they subsequently find each other and do communication from then on. And the problem when I sort of was introduced to this about 8 years ago was that there were this kind of personal devices that were becoming very popular, Bluetooth and Wi-Fi and so on. And of course, you need to, as part of this first connect initialization, you want to do security associations so that they can not only find each other, but they can also communicate securely. And because it's a security association, you want to do it as securely as possible. But there was no infrastructure. There was no expert administrator who would set things up for you. You are an ordinary user, maybe a small child or a grandmother who goes to a shop and buy a headset from one manufacturer and buy a phone from another manufacturer, and you need to be able to set things up. And these are ordinary users without any expert support. But they're also dealing with very cost-sensitive devices, right? So we talked about putting an LED on a device, on a phone, and if that was a no-no, you can imagine like a headset which costs like 20 euros. And doing any kind of additional hardware that is necessary for making this process easier is not going to fly. So you have to deal with doing this securely, by ordinary users, and without driving up the cost. So this was kind of the problem area. And at that point, the situation was the following. There were prevalent mechanisms. There was Bluetooth pairing, there was Wi-Fi setup, but they were not easy to use or understand. So on the left, you see the screen that you would have seen if you wanted to set up a wireless network on an XP machine. On the right, you see what would have happened if you wanted to pair your headset with another device. So typically, first of all, you would see a list of devices from which you have to choose your device. Those devices have some standard default names out of the factory. So if you scan, you might find 10 devices called Nokia N95 at that time. Now you might find 5 devices called iPhone 5. You have to know which one is yours. So there's a selection problem. And once you have selected, then you ask for something like a passcode. And one of the colleagues of mine who does user research or usability research told me that when they did subsequent sort of interviews, many users thought that when they asked for the passcode, they should type in their ATM passcode, because that was the only passcode they knew at that time. So these mechanisms were not intuitive or easy to use. They also happened to be not very secure. So there were papers that talked about how to compromise the security of Bluetooth. There were even more papers about how to compromise the security of web and other Wi-Fi security mechanisms. And some of the reasons were, for example, for Bluetooth, security was designed in the late 90s when there was some concern about whether the mobile devices could do public key crypto, and therefore they designed mechanisms that just use symmetric keys. And many of the attacks were exploiting this fact. But neither of them would have been a problem. Okay, it's hard to use, and it's possible for some academics to break the security, but neither by itself would have really caused any problem. So it so happens that when you have a system that is widely deployed, that uses that made some assumptions about security and usability, but and assumptions about certain use cases, and you try to use them in a different scenario where you think that the usability should be improved or security should be improved, trying to retrofit those mechanisms is kind of might not always lead to a good conclusion. So this is an example from about 10 years ago where there was a product which is a kind of a set-top box. So you buy this and connect it to your TV, and it's a Bluetooth-enabled set-top box. And the idea was that if you have, this was the time when camera phones were becoming popular, so you could take pictures on your camera phone, and then you could connect automatically to the TV, and you can view the pictures on a big screen. And of course, this process has to be very intuitive and easy to use. But all they had was Bluetooth, so they decided that they will have a default password so that we don't have to go through the trouble of asking users to do the pairing. And the default passwords are 0000. And this news item refers to the case where somebody turned that TV on and found the neighbor's pictures showing up on their TV. So naive mechanisms naive ways to try to improve usability can damage security. But the reverse is also true, that when you try to take these mechanisms which were not intended to be used in relatively high security use cases, and then you try to shoehorn in better security, you might be really compromising usability. So this is a page from a manual for a car kit. So a car kit is essentially a GSM phone, except that it doesn't have a SIM card. So you can buy a car kit and then attach it to your car. And if you know how GSM works, you have a shared secret in your SIM, and the operator has the same shared secret. Whenever you turn your device on or whenever you move into a new area, your phone and the operator network engage in a sort of authentication key agreement protocol using this shared secret as a master key. And at the end of the protocol, both sides get session keys. And the session keys on the network side are given to base stations, and session keys on the device side are transferred from the SIM to the mobile device. And the session keys are then used to protect the integrity and authenticity of communication. So phone calls are protected like this, and so on. So session keys are the ones that are the sensitive information, right? If I have your session key, I will be able to make calls that will be billed to you. So what the car kits do is they don't have a SIM, but they have otherwise a fully functional GSM phone. And the idea is that when you walk into your car, your phone will, if it had already been paired with your car kit, it can establish a secure connection and transfer the session keys from the phone to the car kit. And thereafter, the car kit can essentially act as your phone. It can receive calls, use the car speakers, it can let you dial, make new calls using car peripherals. It's a nice safety mechanism so that you don't endanger yourself by talking on the phone while driving with one hand. You can drive with both hands and still use the car kit. So it was a popular, and I think it still is a popular device. But it has this very sensitive thing that your phone is going to transfer session keys to the car kit. And therefore, if you end up transferring the session keys to the wrong car kit, then any calls that are made by this other guy will be billed to you. So they decided that this ordinary Bluetooth pairing using 4 digits is not enough, because they were, as you saw before, they were vulnerable. Anybody who records the Bluetooth pairing exchanges will be able to break the long-term key. So they had a requirement like, and every time you connect, the car kit will show you a 16-character alphanumeric code, and the user has to type this into the phone. This was like 2002, so you had probably just a numeric keypad, and you had to do that within 30 seconds. So it sounds like this Dilbert cartoon that we saw is actually close to reality, that if you want to make something secure, it's going to be hard to use. And the cost here is that if you buy a headset and you try to pair with your phone and it doesn't work, you call the helpline of Samsung or Nokia, or on the other case like the headset manufacturer. And these companies are selling these devices at very low profit margins, and they don't want to hear from you. If you call them, that might wipe out the profit that they made on this device. So the thing that motivated action in this case was not the fact that some academics had published papers, not the fact that the usability was awful, but the fact that this was starting to be a problem, that there were calls to the customer support. And not only the device manufacturers, but also Microsoft, because you have you have Windows running on your PC and you couldn't connect your phone to your PC, you call Microsoft help desk, and Microsoft doesn't want to hear from you either. So in 2006 or so, many of the companies got together and wanted to revisit these first connect protocols like Bluetooth and Wi-Fi and so on, and wanted an alternative that is, first of all, it should be intuitive so that you don't call the help desk, it should just work, and it should be inexpensive, it should not cost any new hardware or additional development deployment costs, and also maybe it should be, while you are redoing this, it might as well be more secure than before. And there were two problems to solve. One is this discovery problem that I told you about. So if you scan for the devices and there are 5 iPhone 5s and you have the trouble of deciding which iPhone 5 is yours, that should be solved somehow. So it should be easy for you to figure out. That's not a security problem, that's just a usability problem. And second one is that once you have figured out what the right devices, then you want to run a protocol with them that, in addition to setting up other things, it should also set up a shared session key or a shared key that you can use subsequently. So essentially, we are talking about authenticated key establishment. This was the problem to solve. On the other hand, there was one sort of redeeming feature about this use case is that typically when you do an authenticated key agreement protocol, you are talking about two peers who are maybe far away, right? Maybe a client and a server which is far away. Here, it's normally the case that the two devices are physically identifiable. It could be sort of obviously physically identifiable, like a phone and a PC, or a headset and a phone, or it could be somehow logically physically identifiable, that you have an access point which might be not visible, but you have a PC that controls the access point, and then you have a new PC that you want to admit to your wireless network. So we can turn this into our advantage. So at that time, the key establishment protocol, so if you kind of classify key establishment protocols, authentication for key establishment in the following way. So key establishment can be either key agreement, so that there is some protocol, after that both sides get the key, or it can be simply key transport, that somehow one side picks a key and gives it to the other side via some secure means. And if it is a key agreement protocol, it can be based on asymmetric key, like Diffie-Hellman, or it can be a symmetric key protocol like what Bluetooth and Wi-Fi were using at that time. And in each case, it can be either authenticated or unauthenticated. And authenticated in this case means that they are the two devices that the user intended to pair, and not some other two devices. So the existing protocols sort of fell into this category. They were not using asymmetric crypto, so they were symmetric based authentication protocol. They were authenticated, but it's the user who has to authenticate, and users have cognitive limitations, right? So users cannot handle 128-bit keys or anything like that. So the authentication was using short keys, and typically 4 to 6-digit keys. And that's why if you do a key agreement with short keys and it only uses symmetric crypto, then it's vulnerable even to passive attackers. Somebody who records the Bluetooth pairing session would be able to recover the key that was agreed, and after that can pretend to be one device towards the other. And also can recover all subsequent communication. So the intent was that we should at least move from here to key agreement using asymmetric crypto, because that will be secure against passive attackers. And then if you can do authentication on top in a reasonable way, that would be good too. So how do we authenticate key agreement in this kind of scenario? So essentially, there are two ways. Well, there's essentially, you need some way, some other channel than the channel that you are using to authenticate the key agreement. This is not strictly true, and we'll come to that later, that you can also try to use the channel itself to authenticate key agreement. But for the time being, sort of take my word that if you want to authenticate the key agreement over Bluetooth and you don't trust Bluetooth, then you need the help of some other channel which you can use to authenticate key agreement. Similarly, if you want to authenticate key agreement over Wi-Fi, then you need some other channel. So this channel can be one of two possibilities. It can be the user himself or user herself, or it can be some other out-of-band channel. And there are many, many popular out-of-band channels. People get creative when they start to think about out-of-band channels and propose all kinds of out-of-band channels. The popular ones are like near-field communication, like NFC, that you touch two devices and you use that as the out-of-band channel. But there can be many others as well. OK, so in this talk, I'm going to primarily focus on this user-assisted channel, because that's something that is guaranteed to be there always, that there is always a user involved. Okay, so how does, what do we mean by key agreement? So essentially there is A and B. These are the two devices that the user intends, and they do a key agreement. So it could be Diffie-Hellman, but conceptually they are just exchanging public keys. And that happens over insecure in-band communication, like Bluetooth or Wi-Fi. After that, we have to do an authentication step, and the authentication step might also involve some messages that are exchanged over the insecure band, insecure communication, but then it might also involve the user, because they are relying on the user as the out-of-band channel. So the devices might either ask something from the user or give something to the user, and that would hopefully lead to authentication. So it doesn't have to happen in this order, but these are the kind of two blocks. You do key agreement, and then you do want to do authentication. But there are some constraints now. So the first constraint is what we already touched on, that the bandwidth of these purple channels is low. We are talking about 4 to 6 digits. We cannot expect users to handle more than that. There's also directionality issues. So maybe some of these channels are only one way. Like, for example, if this is a display and we are showing something to the user, we need a display to show something to the user. If it is like an audio channel and one side has a microphone, the other side has a speaker, then you can transfer information in one direction, but not in the other direction. And the security properties might also vary. So sometimes you need integrity, sometimes you might need integrity and secrecy, and depending on the channel, it may or may not support. So there are constraints about what this out-of-band channel can provide. Okay, so the peer discovery, the problem of finding which other device to do the first connect protocol with. So remember that this is not a security problem, it's a usability problem. This is the problem of choosing the right iPhone 5 among 5 iPhone 5s that you see. So that's easily solved by essentially what's relying on the fact that we assume that the user can identify these two devices, and therefore the user can do what's called user conditioning. You can do some action on both devices. So if the user says, okay, start pairing on both devices, then one iPhone 5 can put its hands up and say, I'm now ready for pairing. And the other device can then look around to see how many iPhone 5 devices are ready for pairing, and then pair with the one that, hopefully there's only one, and you can pair with that. So again, this is not a security problem. We have to do authentication later on, but it reduces the number of cases where the user will be asked to choose. So the real problem is how to authenticate key agreement, and relying on the user as the secure channel. And in the end, there were two ways to do that. One is to ask the user to compare sort of checksums of the protocol run on both sides. So this is sometimes called short authentication string protocols. And these are non-secret codes. They're like checksums. The devices run a protocol. At the end of the protocol, they calculate some short checksums, and they show it to the user and ask the user to compare. And if they have been in fact talking to each other, then the checksum would be the same. If there is a man in the middle, then the checksum hopefully is different. So that's one class of protocols, and this is the one that we'll look at a bit more detail. The other class of protocol is like using just a passkey, like in the old Bluetooth model. So remember that we are thinking about or talking about standards here, not an academic paper. So that's why it was not enough to just publish a paper that shows how to do short authentication string, because in reality, if you want to do a protocol like this, you have to be able to show the short authentication string to the user. And you might not always have this possibility. If you are connecting a headset to a phone, the headset may not be able to easily show a short string to you. It could maybe speak it out, but it's not a very easy solution. So a standard has to cater to all possible combinations, and that's why, as you will see later, the current standards actually support these two, but also support a couple of other methods. Okay, so we want to do authentication by comparing these short checksums. And we are limited by the fact that the user bandwidth is small, so we are talking about 4 to 6 digit checksum. But the security requirement is that the fact that we are using a short key should not hamper security in any significant way. And in practice, what that means is that there should not be, against offline attacks, so somebody who records the pairing protocol and then puts whatever computing power they have, there should be standard security against them, because there is no way to there's no limitation on how much computational power they can put against this. For a man in the middle, we want good enough security, and I'll try to explain what I mean by good enough security. So if you are trying to pair two devices, then there is a certain amount of time before which the man in the middle should succeed. If he doesn't succeed, then the user might not wait for 1 hour for the pairing to complete. So we can take advantage of this. We can say the attacker should succeed with a reasonable number of tries, but we don't need to give unlimited power to the attacker at that point because the transactions are limited in time. On the other hand, we don't know anything about the computational power of the attacker. So it should not be the case that the attacker can do lots of pre-computation or lots of post-computation and break this security. So it will become a bit clearer later, but this is kind of the framework that we are working against. Okay, so how do we do authentication by short string comparison? So let me first put up a kind of a straw man protocol, which is of course not secure, and then we can see how to strengthen this. So as a kind of first draft, we could say, well, they exchange public keys, pka and pkb, and then they so if you have pka and pkb, let's assume that you can do a calculator session key from those. So if you have Diffie-Hellman, just exchanging some public values is enough. If you have some other key, then you can have a little bit more elaborate protocol, but effectively if you exchange public keys, you can agree with come up with a session key. And now each party calculates a checksum, which is essentially a record of this transaction. So it includes the identities of these two parties. Every party includes its own public key, and then it also includes the public key that it thinks belongs to the other device. So in this case, I use this prime notation because A knows its own public key with certainty, but pkb is something that came over the insecure channel. So it may be B's public key, or it may be somebody else's public key. We don't know. And similarly, B will calculate a similar checksum. It knows its own public key, and then it has this public key that allegedly belongs to A. So it can calculate these two checksums, and then show them to the user. And if they are the same, the user can confirm that it's okay or not okay. And the requirement is that it should be identical if A and B are talking to each other. If A and B are talking to somebody else, a man in the middle, then these checksums would be different. But the checksums have to be necessarily small. So we are talking about 4 digits or 6 digits. So this is, of course, not secure. A man in the middle can defeat this, and I'm sure you already see this, but we can sort of see how that would go. So if there's a man in the middle, setup is as before. When A sends the public key, C can intercept that public key. C is the man in the middle, and then send its own public key pkc1 to B. B at that point will reply with its own public key, and it will proceed to compute this checksum where it takes A and B and its own public key, and then what it thinks is A's public key, which is actually pkc1. So it's going to compute a checksum like this. But at this point, C can also compute the same checksum because it has the same information. So it can compute exactly what B prime B would be. So now in order to win this game, what C has to do is to find a public key pkc2 such that this particular hash would be the same as that one, right? Because the user is holding these two devices A and B and expecting to see if they would show the same number or not. Okay, so the C's job is essentially to guess values of key pairs and then try different values of pkc2 until this succeeds. So maybe the attacker has already pre-created a large number of key pairs, and then it's just going to try essentially each of this trial and error step would cost one hash function. So this is of course easy to do because once he finds the right public key, he can send it to A, and A would now calculate a checksum that includes pkc2, and because of the way C chose this pkc2, these two numbers are going to be the same, and the attacker is going to win. Okay, so like I said, each of these guesses would cost one hash, and if you are talking about n-digit checksums, then in the worst case you have to do 10 to the n guesses. In the average case, you do half of that. But each guess costs only one hash, and in a modern PC, this was like 5-6 years ago, could do 100,000 max in a second, you can imagine. So something like brute forcing this can be done in sub-second time. Okay, so how would we strengthen this? So remember that our goal was to try to make this pairing protocol easier, and doing a kind of straightforward approach didn't work. So now we have to revisit the protocol and see how we can make the protocol stronger so that it supports this usability advantage that we want. Okay, so we do key agreement like before, but now we ask A to pick a long random string, so a 128-bit random string, and then calculate a commitment to that. So we want two properties from this commitment. The first thing is that, so commitment is a function that takes this random secret value and computes a commitment HA. In practice, it can be a hash function. So the two properties that we want are, the first is called a hiding property, so that given HA, it reveals no information about the secret that went into this computation. And the second one is what's called a binding property, so that once A releases HA to B, so A is going to send this HA to B, A cannot change its mind about what RA is. So it has to pick an RA, it commits to the value, and then it gives the commitment to B. After that, A cannot change its value because it's, as you will see, B will later check to see if this commitment matches the value that it committed to. So A sends HA to B, the commitment to B. B at that point cannot tell any, the HA just looks like a random string, so it just stores that, and it chooses its own random string RB, and then just discloses that to B, that to A. At this point, A will release its own RA that it committed to here, and B will now check to see if this RA matches this commitment, and it can do that easily, right? It repeats the same computation. It takes its RA, or RA prime, because RA is what came over the network. It hashes this identity of A and RA prime, and then see if the result is the same as what it got over the network here. Right? So if they are the same, then it continues. If not, then there must be something wrong here in aborts. So what we have done at this point is we have forced A to choose RA without knowing what RB is, and similarly B chose RB without knowing what RA is, right? So B at this point got HA, but because we assume that the commitment is a hiding commitment, HA doesn't reveal any information about RA. So B had to just choose a value of RB randomly. And similarly, because of the binding property of HA, A chose RA here, and it committed to it. After that, it got RB, but it can't change its mind about RB at this point because it already committed to RA here. So if it changes its mind, that will be caught in this step. So we have independently, we have forced each party to choose this RA and RB, which are long secret values, long random values independently. So now we can calculate the checksum by having the same things as before, but also these two values. So remember that earlier the attack was that the attacker could force one party to commit to all its input, and then had some time before it was forced to commit to its own inputs to the other party. Right? Now, because we are forcing these two parties to commit to all their inputs, an attacker would do the same. The attacker will have to commit to all its inputs before it finds out what the other party's contribution was. So now the rest of the process as before, you show the checksum to A and B, and if they are the same, the user would approve and the pairing would succeed. And so H is like should be hiding and binding commitment, and in practice it can be a SHA function, a hash function, cryptographic hash function. And similarly, this H is something that should change whenever some input changes with uniform probability. And in practice, again, that's a hash function where whose output is truncated. So what's the strategy for an attacker now? Since the attacker can't do any pre-computation, it doesn't matter how much computation power the attacker has. The only thing that the attacker can do is to just guess some value of RA and then hope that these two numbers would be the same, even though the public keys are different. And there is a probability that that would happen because these checksums are small, right? They are 4-digit checksums. So if you have a L-bit checksum, then there is a 1 in 2 to the L chance that he would succeed. So we kind of, this is not really unconditional, but we can call it unconditional in the sense that the attacker's chance of succeeding doesn't depend on any computation power it has, except this key agreement is probably a computational key agreement protocol, so it's not unconditional in that sense. But his best strategy is to just guess and see if he succeeds. So this is a protocol that that we came up with in the process of revisiting Bluetooth, and Kaisa Newberry, my colleague, and her student had a formal proof of correctness of this protocol, and this actually ended up in the specification. So what this now has achieved is that you can do a short string comparison and to authenticate key agreement in such a way that it doesn't matter what the what computational power the attacker has. The attacker could still try different values, but he would succeed with some probability. But since this whole process will not last forever, it was okay to have this kind of 2 to the minus L, because it's 2 to the minus L every time. There is no accumulation of success probability. Okay, so like I said, yes?
What if the man in the middle controls the fast communication, whether it sends to the user the opening out of the
Right, so I didn't actually explicitly mention this. So we assume that this is this auxiliary channel that is not accessible to the attacker. So that was the kind of whole point about you have a in-band insecure channel, and then you have an out-of-band that you assume is not accessible to the attacker. If the attacker has control of that, then of course none of this works, right? So in practice, what this means is that you have to assume that there is no malware on the devices, right? If there is malware on the devices, they can show whatever number they want for the user. But
and also, if you have this kind of channel, then use this channel to coordinate the key.
But so this is a channel. So imagine that this is a display that's showing 4 digits. Right? So this is a display that's showing 4 digits, this is a display that's showing 4 digits. So we can assume that as long as there's no malware on these devices, the attacker can't control this. But we can't really do a key agreement using this because it's only 4 digits in each side. So we can use it to authenticate key agreement. Okay. So like I said, in a standard, it's not enough to just have this one variant, because it requires, for example, that there is some output mechanism that these devices can talk to the device. So there was also a variant for using a short passkey, and I'm not going to go through this, but the step would be something like, A chooses a passkey, shows that to the user types that passkey to be. It's a short passkey, 4 to 6 digits, and then there's key agreement, and then there's some kind of opening protocol. So the Naïve protocol is insecure, and the secure protocol that's deployed again uses this idea of sending commitments first and opening commitments later. I'm not going to go through this, except that I want you to point out a couple of things. One is that, so essentially how it works is that you transfer this password once, and then for every bit in the password you do a commitment, send commitments, open commitment protocol, so that you prove knowledge of, both sides prove knowledge of that they know the same bit. And if you do it 20 times for 6 digits, then there is this same kind of chance of success. This particular variant with the protocol is such that the passkey must be a one-time passkey. You cannot reuse passkeys. So when Orr introduced Steve Elevin, you said that there is this password authenticated key exchange protocols, which are actually designed for passwords that can be reused again and again and again. Bluetooth specification didn't use those protocols. The actual reason is that because many of those protocols were encumbered by patents. And so they came up with this alternative, which has this limitation that it's a one-time protocol, but it's not the same protocol as, I think it's not Bell Labs that had the patents, but it's some one-man company had patents. And whenever there's a standards organization with big companies, they never want to use a solution whose patents are held by a one-man company, because the big companies can be held hostage by this. So that's essentially what we are doing is password authenticated key agreement with this caveat that this is only a one-time passkey. So I'm not going to go through this, but the spirit is the same. Passkeys have to be short. You have to do authenticate key agreement without assuming any limitations on the computational power of the attacker. So if you go back to this, this classification now, so we did an asymmetric crypto-based authenticate key agreement. This authentication is by integrity checking, where we were using short string comparison, and this is kind of this one first user assisted protocol. And the second protocol was again authenticated product key agreement using a shared secret. This is the one that I didn't explain fully, but you have pointers in the slides if you want to know more. Okay, so these are both protocols are relying on the user, and there is some expectation of hardware. So for example, there should be some displays or keypad buttons depending on the variant that you're using, and those may not be always satisfied. And there is also this issue of usability, right? So would people enter these passwords correctly or do the comparison correctly? So having something else like an out-of-band channel which just removes the burden from the user completely would actually be desirable. So the specifications also use this kind of out-of-band variants. So out-of-band is you assume a channel that is long enough and that has enough bandwidth to exchange these checksums or exchange a passcode. So it has to be a physically secure channel, and the goal would be of using the channel would be to minimize user involvement so that there is less risk of any user mistakes or user errors. The essential protocol looks something like this. You do key agreement, and then you do some exchange by these channels. And you can sort of imagine how one would use this channel, right? So the protocol that I showed before, instead of showing two checksums to the user and asking the user to compare, if you had a secure channel like NFC, you can just use this NFC channel to exchange these checksums. Or if the channel bandwidth is big enough, then like you said, you don't need to do anything else. You can just exchange public keys via NFC as a channel. So we can sort of augment this protocol by saying that if you had a channel, then you can do these key commitments via out-of-band channel itself. So you don't need any of these fancy protocols, just exchange public keys via this channel. If it doesn't have enough bandwidth, you can do the same protocol, but instead of relying on the user, you can exchange the checksums via this out-of-band channel. And similarly, if you have authentication by shared secret, then you can use the out-of-band channel to exchange the shared secret. So these are the kinds of, and you can have some hybrid variant as well. So out-of-band channels, of course, come with a cost. So 6 years ago, people were still worried about NFC. NFC would be the ideal solution to this, but people were worried that NFC might not be widely deployed. And in hindsight, it turns out to be true that even today, NFC is not widely deployed in all the devices because it adds a cost, and unless the cost is justified, it's not going to be there. So I mean, there are sort of advantages and disadvantages. You can use the user, which might come for essentially for free, but user might be prone to making mistakes. You can use an out-of-band channel, but you might not always have it. So the best solution for this, of course, would be to use something that doesn't require any out-of-band channel and doesn't involve the user. And intuitively, it seems like this wouldn't be possible, right? But there are some developments which actually makes it possible. So I list a few of them here. So one is called in-band integrity checking. The second is called extracting information from a common radio environment. And the third one is spatial indistinguishability. So I'm not going to explain all of these because I don't have time, but just to give you an idea. So common radio environment relies on the fact that if I have my phone here and my PC here, they see a radio environment, right? So they see Wi-Fi access points, Bluetooth device, and so on. And what they see depends on the place where they are. So your device might not see the same thing that my devices see. Whereas if my devices are close together, they might see more or less the same environment. And what these proposals do is to try to extract entropy from what you see. And it relies on two things. One is that somebody who is sort of further away wouldn't be able to extract the same key as these two devices would extract. And also somebody who comes here later on wouldn't be able to guess what key I would have extracted. If you can satisfy this, then all you do is you say, okay, I want to pair these two devices, press a button, they extract the same key. Maybe it's not exactly the same key, but they can do some kind of key amplification to remove errors, and they can end up with a shared key. So there are some papers that propose this kind of method. A more interesting one is this in-band integrity checking. And the idea in in-band integrity checking is that so the way my device communicates with your device over Bluetooth or Wi-Fi is by manipulating the energy in the that's its output, right? So if I want to maybe have a 1 bit in the wire, I would transmit some energy. If I want to have a 0 bit, I would be quiet. And so if it's a naive encoding scheme like that, of course an attacker can manipulate this by whenever I'm quiet, he can inject energy. But suppressing energy is harder, right? If I have a 1 bit where I'm communicating 1 bit by transferring some energy, it will be harder to suppress that for the attacker. So what these guys in this in-band integrity checking essentially do is to say use an encoding mechanism so that every logical bit is encoded in such a way that over the wire there's always a physical bit, a physical 1 bit. So you can do something like Manchester encoding where 1 is encoded as 1 and 0 is encoded as 0 and 1, so that whatever I am transmitting there's always some energy, and the attacker wouldn't be able to manipulate this without being detected. If this can be done right, it gives the nice option that there is no need for extra hardware because you're using the same in-band. There's no involvement of the user, but you can actually do authenticated key agreement. And we'll come back to that a little bit later. So getting back to the story of what happened in 2006, so in the end, you could sort of build out a classification like this for key establishment for FastConnect, and different standards bodies ended up using different of these. So this stands for Bluetooth, this stands for Wi-Fi protected setup, and this stands for something called wireless USB, which at that time was thought that it will become popular, but it hasn't. So this is the same thing that sort of summarizes this now. So every standard body used multiple of these. So for example, Bluetooth, if you have paired a Bluetooth device now, you would know that you have this short string comparison. If you want to pair a Bluetooth phone with a laptop, you would see these two numbers that show up. So Bluetooth supports short string comparison, short pin, but also NFC. This wireless USB was supposed to have a short string comparison, and then just by connecting a USB cable, you can pair two devices. All of them, or actually these two, also support essentially unauthenticated Diffie-Hellman, because there might be cases where you simply can't afford any kind of display or input or any NFC or anything like that. And in those cases, all you do is protect against an active adversary. You activate pairing on both devices, you do key agreement, and if there's an active adversary at that time, then you lose. But if there is no active adversary at that time, then you have a secure channel. So this is like this kind of trust on first use type of thing, that if you do the first connect correctly, then you can rely on the security. So there are a couple of pointers here if you are interested in more information. So the situation today, just to close this, is that these are widely deployed, but the revelation for me, which I wanted to sort of make the point of this, is that we started out with the goal of improving usability and security, and improving usability is not just a matter of a better UI, that you may have to actually revisit the underlying protocols and then try to design a better protocol. Did we actually improve usability? This is hard to know. So we actually did some usability testing, and the results were kind of mixed. So if you show two numbers to users and ask them, are they the same, at some point they actually stop checking if they are the same. They might just click through. So in that sense, I think this is still an open problem. And I think what is promising is what we just talked about before, that if you can do in-band integrity checking, which removes the user and doesn't incur any new costs, that might be a way to solve this problem when it reappears again. And there have been some proposals in the literature that tell you how to do this. So these are the screenshots that you would see if you were trying to pair a phone with a PC today. I think all major operating systems support this, and pretty much all mobile operating systems also support this. So before I close this and go to the next topic, I sort of want to give you one cautionary tale. So if you remember this one-time passcode protocol, it said that the password authenticated protocol said that the passcode must be used only once. And the specification is very clear about this. It also tells you if you have to reuse a password, then there are certain safeguards you could take. And of course, not all implementations do this. And this is somebody between Christmas and New Year a couple of years ago decided to try this out and noticed that they can actually break a large number of access points out there which were implementing this protocol because they were reusing the same key again and again and again. So there is a pointer to that if you are interested. Okay, so that's the first use case. And now I want to tell a bit about the second use case that, that again illustrates this tension between usability and security, which is this, this problem of granting permissions to application. So if you use a smartphone, if you use Android specifically, then you know you are familiar with this problem. And the problem is the following. So traditionally, access control in operating system is there are subjects in the operating system, and access control regulates what the subjects can do. And in a multi-user system, the subjects are users. So access control policies are about what users can do. But in mobile devices, there's only one user, and the subjects are actually applications. You might download one app from some app store. Some apps might come with the system. And even though they are acting on your behalf, they are all not the same. So you need to be able to say which application is allowed to do what. And this is the basis for all the popular mobile software platform security architectures. And they do this access control using this notion of permissions. So they identify applications as principals and then say assign permissions to applications. So permissions are like, you can think of them as tickets. So you have a ticket, and this ticket allows you to enter this door. So you can have permissions that say you are allowed to access the GPS, or you are allowed to access network communication, or you are allowed to access users' contact list. So the way the access control is managed is by assigning permissions somehow to applications, and then at the time when an application wants to access something, you check to see if it has the requisite permission. So the challenge is, how do you grant permission? How do you assign permissions to applications? So essentially there are two ways, right? So one is the kind of authoritarian way, where I say somebody is going to decide what's allowed and what's not allowed. The other one is to just give up and say let the user decide. And both have pros and cons. So the user decide approach is taken by Android. And if you have used an Android device, you would see something like that. Whenever you install an application, it might ask you questions like this, like this is the UI some time ago, this is the current UI. But essentially the information is the same. It asks you, do you want this application to modify, delete USB storage contents? An ordinary user might have to, based on this information, has to decide, should I allow this application to do this or not? And the tension here is that if the application actually needs this and you don't want to grant this permission, then it will not work and the installation will not succeed. And we had a paper a couple of years ago where we looked at, this is not just a mobile device problem, there's also the same problem if you want to install, so let's say, Chrome browser extensions, or for example, Chrome browser extension. So we looked at a bunch of cases like this, and it was clear that the information that's conveyed to the user currently is not enough for the user to make a sensible decision. On the other hand, you could decide this centrally, and this is the Apple way. Apple used to not ask you anything. They will decide for you because they know what's good and bad. So even they are sort of backtracking on this, because so recently I think Apple would ask you, or iOS would ask you runtime prompts if an application won't access your personal data like photos. But they try to minimize this. So there are sort of advantages and disadvantages in both, right? So if you want to punt everything to the user, you can be sure that the policy that you come up with is really personalized for that user, because it's the user who makes the decisions. So you don't have to have this problem of one-size-fits-all policies. But it's hard to use. Users, of course, make ill-informed decisions because they don't have enough information. So they might decide that an application needs access to USB storage, even though they don't really understand why that is so. And the last problem is this habituation, that if you ask this again and again and again, people stop reading what the prompt is and just click through, right? And this has been shown again and again, that most people who do Android installation don't actually understand, or not even understand, but don't even bother to read what the prompt is, because they want to install an application and they just go through with this. On the other hand, if you decide centrally, potentially it could give ease of use. So Apple could say that there is no problem in using iOS because there are no prompts, but they have to then decide the same policy for everybody. And there might also be liability questions that if Apple allows an application to be installed and the application does something bad, who is liable? Of course, you might argue that we are in the software industry. What liability? Nobody takes any liability anyway. But it's possible that if a decision is made by somebody else on behalf of the user, then there must be some liability. And this is, I think, one reason why even iOS now tries to punt the decision of access to personal data to the user. Okay, so what is the cost of this? Well, if you have a system that makes it hard to use, there might be user dissatisfaction, which is maybe not so unobvious. So the question is, how do we go about improving permission granting? And what I'm going to walk you through is some of the solutions that have been proposed in the literature. So first of all, if you are going to prompt, you could try to give more contextual information about why that prompt is made. So there are a bunch of papers that go in this direction, that they try to annotate the prompts with some useful information. And we'll talk about how where did this information come from. The second one is, so you saw earlier that Android asks you prompts at install time. iOS and Windows Phone now ask you at runtime. But they always, so Android always asks you at install time, and Android and Windows Phone always ask you at runtime. There might be ways to sort of decide what is appropriate given the kind of permission that you want to install. So install time versus runtime depending on the type of permission. And the third thing is that, so the third and fourth are like, let's not ask the user anything, let's not prompt the user anything. That it might be possible in some situation to implicitly figure out what the user wants by monitoring how the user interacts with the device or the application. And that requires some kind of trusted UI, and I'll give an example of that. And the last possibility is, of course, just grant what the application wants, but keep track of, keep the application accountable in some way. So if the application wants to, the ability to change the ringtone, you let it change the ringtone, but then make it visible to the user should the user ever want to find out who changed the ringtone, so that the user can act on it afterwards. Okay, so the first one is annotations. So you want to show information to the user that can maybe help the user make more informed decisions. And there are a couple of ways of getting information. One is that you can actually analyze the application. And the second one is you can get evaluations about an application either from experts or by crowdsourcing. All of these are problematic. So the paper that I'm going to sort of briefly tell you about was something that I think it's from people in CMU, and their idea was that, or the motivation was that whether an application should be given a permission really depends on what the application is trying to do, right? So you can't just unilaterally say that location information is bad. If an application asks for location information is bad. If an application like a navigation application asks for location information, that's a natural thing. Whereas if a flashlight application asks for location information, that might be a privacy breach. So their definition is that privacy is breached or at risk if the user's expectations are not met. So if you remember Claudia's talk yesterday, this is a bit problematic because the user might not know might not have the right expectations. But on the other hand, if the user's expectations are not met, then you can say that there is potentially a privacy risk. So what they did was they had a training phase where they recruited a bunch of users, and they told these bunch of users what an application did with the permission it asked. And then they annotated the permission prompts with the information that described the reactions of these users to other users, so that when other users try to install that, it told them about these reactions of this first set of users, as you'll see in a minute. So how do they get information about what the application does? So first of all, you can every application that asks for permissions, you can get the list of permission from the manifest, and then they can use a kind of analysis tool, a static analysis tool, or other kinds of analysis tools to figure out what they do with these permissions. So in this particular case, they used an application or a system called Taindroid, which tracks where data goes. So if an application takes the location and then later sends this location to via the network, Taindroid can keep track of this. And in the next step, they showed this information to the user and asked about their reaction. So they asked questions like, do you expect this app to use location information? Or are you comfortable with this application using asking for your location in order to show you advertisements that are targeted for your location? And then what they did was they used the results of these this first phase to show this to other users. So now they changed the installation screen so that in addition to asking for location permissions, it would say things like 95% of other users were surprised that this application used approximate location to mobile ad providers. So rather than just asking permission information, they tried to say this other group of users had this kind of reaction. And they, of course, did a user study to validate this. And not surprisingly, they say that compared to a control case where users were using the standard installer to install applications, when they were given annotated prompts like this, the risk of installing a misbehaving application like this brightest flashlight, which is a flashlight application trying to ask for your location, was significantly reduced. Okay, so again, you can quibble with each part of those, each of the steps that they did, but this is sort of one way to say, here is how you annotate your permission prompts to try to help the user make a more informed decision. The second topic, second item we had on the list was time of granting. So like I said, Android asks you upfront, iOS asks you at the time of access. And these both have pros and cons. So asking at install time, the user is not doing something. The user is actually installing the application. So it's not disruptive. The user can afford to think more about what they are doing. On the other hand, it provides no contextual information. So if you ask that should this application have access to storage, you might not even know you might not be able to make a sensible decision whether it really needs access to storage. On the other hand, if you ask at runtime, there can be more contextual information. Let's say that you took a photo and then you want to store the photo, and the application system asks, do you want to access this application to your photo album? The user has more contextual information to decide whether this should be done or not. It can also be more fine-grained. If you're asking at install time, you can only ask a limited number of permissions, right? Remember that users have cognitive limitations, so you can't ask about 100 permissions. Android actually has something like 112 permissions, but in the prompt they group these permissions into some small number of groups, and then they can ask about groups of permissions. Whereas if you are asking a runtime, you can ask a very precise question that is fine-grained. On the other hand, you have the risk that the user is trying to do something, and if you at that time you pop up a question and ask, do you want to do this? Do you want to grant this permission? They might see this as a kind of something that is intruding in their workflow, and therefore dismiss it by saying that, no, if I want to continue playing this game, if that's possible only by granting the location permission to this application, I might as well just do this, because what I want to do is to play the game. And it can also be intrusive, because if you keep doing this, the users might become accustomed to this and might start to ignore. So again, it has like pros and cons. The third one was this implicit permission granting. So this is based on the idea that sometimes the way the user interacts with the system is enough to tell what the user's intents are. So imagine that there is a kind of a drag and drop style UI, right? So if you want to maybe you have an image editing application, and the way you start to launch this image editing application is you drag an image and drop it onto the application, and the application has access to this. So if you have a permission system that is governing this, at that point, it's actually not necessary to ask the user, do you want this application to access your photos, if what the user did was to drag one of his photos and drop it in the application. provided that you can trust the UI. So you must make sure that the application couldn't have somehow forged this interaction, or the application didn't fool the user into thinking that he's dropping the application, the file on one application but not on the other. And this is why if you want to do implicit permission granting, you need hardware support that makes sure that this UI interaction is neither forgeable nor obscurable, in the sense that the user thinks that it's interacting with one application, but it in fact doing that with another application. So there is a paper, again a couple of years ago, where they tried to apply this to permission granting for mobile operating systems, and their idea was that again permission granting process should be done in context, so that users can sort of decide, and rather than giving blanket permissions like, should this application have access to your camera, which means that it has access to the camera from that point forever, you can sort of limit it to say this application should be granted access to the camera when the user wants to grant it access to the camera. And this process should also follow the task flow and not interrupt it and ask the user to do something else. So their idea was that these resources would have some kind of GUI representation, which they call an access control gadget, that can be imported by an application. So if my application wants to use the camera, rather than asking for camera permission, I would ask access control gadget for the camera to be embedded in my application. And what the trusted UI guarantees is that whenever an application embeds a gadget like this, that cannot be obscured. So you cannot put another thing on top and fool the user into thinking that he's clicking this other thing, whereas the user is clicking really the camera gadget. So you can embed gadgets like this, and if the user presses that gadget, because that will be an intuitive, for example, this photo editor application, taking a picture by clicking a camera icon will be an intuitive action. And the system can then interpret that as saying that, okay, now the user intends that this application should have access to the camera. So this doesn't work in all cases. It will work in the case of camera or some user data. It also has other issues. So the grant can be, of course, controlled in a finer grain. It can be grant once, or you can say grant forever. But what this contradicts with is, if you are going to import a gadget and put that into your UI, that might actually sort of not mesh with the UI style that you have as an application. So these guys thought about this. So for example, now what should the microphone icon look like? If you want to say microphone is represented by a gadget, and if any application that wants to have access to the microphone should be able to import that, you might have many different microphone happen, but there are other applications which essentially do the same thing, but they use different icons that are sort of in line with their UI philosophy or UI structure. So different applications might have something like this, which doesn't look like a microphone, but in that context it's clear to the user that it's about microphone. So when you want to do this gadget in a centralized way, so of course you can't allow arbitrary customization, because that might lead to the user being fooled. On the other hand, if you limit it to a small set of icons or gadgets, that might conflict with developer requirements. So again, this is a research paper. Nobody has really deployed that. It requires support from the hardware to do the trusted UI. But if it were available, this would be one way of addressing this problem. The last thing is this automatic granting of applications, automatic granting of permissions. So the idea here is that if an application wants something, then rather than prompting the user, we can grant that permission, but then have some kind of audit possibility, so that if an application misuses this permission, the user would be able to figure this out later on. So this is intended for anything where the action is not irreversible, right? So if the action is can be reversed without causing harm, then that would be the kind of thing. So for example, network permission, you wouldn't be using this kind of an automatic grant, because if an application wants to use the network permission to send something out, then knowing that it sends something out after the fact is not going to help. But there are other permissions where this might make sense. So for example, they use this for who was responsible for a change. So there is a permission that controls which application can vibrate or access to the phone's vibrator, and this is something that they might fit into this category, that you can let every application vibrate the phone, but when an application is vibrating, you can actually indicate that to the user. You can say, this is the application that's vibrating the phone now, and then give possibilities that if the user notices that and doesn't like that, this is an irreversible, the damage done is not irreversible, so you can take away this permission so that it won't be able to use it or abuse it later on. Another example was changing the wallpaper. So again, you can let every application change the wallpaper, and for changing the wallpaper, it doesn't help to show a notification because the user might not be looking at the device while the wallpaper is being changed, but you can show this, record this information other places, right? So you can have either a notification, or in the settings you can say this is the application that changed the wallpaper the last time. So if a user suddenly wakes up and finds that the wallpaper has changed, then he can figure out which application changed it and then decide to revoke this. Okay, so is this, for example, is this kind of attribution effective? You have to, so now if you show that an application is ringing the vibrator, will users notice that, how to find this information? And the way to do this is to actually do a user study, and I think these people did a user study, and you have to be very careful about doing this user study. So for example, they installed 3 applications which had which asked for the, or which were given the vibration permission, and then they rang the made one application use the vibrator, and then tried to see what percentage of the users correctly identified which application is making the doing this vibration by looking at these annotations that they were putting in the background. And to measure this correctly, they have to make sure that the test is set up in such a way that there were no other cues that the user could have used to correctly identify the application. So if there was only one application with the ability to ring the vibrator, then that might have been the cue. So the laboratory study has to be designed carefully. Okay, so now we saw that you can do permission granting can be done by a user prompt, where you can do that at install time or runtime. You can try to do implicitly if you had the right trusted UI, and you can do automatically but with some kind of auditability. So what is the sort of sensible way to combine these? So there's another recent paper that tried to sort of put this into a structure in the form of a flowchart like this. So when you given a permission that the application wants, the first question you should ask is this permission leading to a revertible action? Can it be undone easily? If it can be undone, then it makes sense to do an automatic grant. If not, then you have to decide, is the damage severe or is it minor? If it is minor, then it might still be okay to do this automatic grant, even though it's not revocable, the harm is minimal. On the other hand, if the harm is significant, then automatic grant is not an option. So then you can ask, is the action initiated by the user, or should it be such that it should not interrupt the user flow? If it's initiated by the user, like taking a picture or starting a recording, then it might make sense to do that via this trusted UI, because the user, as a normal flow, they might actually, it might not be detracting from the user to say start an action. If it is not a user-initiated action, then if the user can change some parameters, it might still be able to, you might still be able to get away with using the trusted UI, but otherwise you have to rely on some kind of user prompt. And the question there is the permission, should the permission work without user involvement, or is it okay to ask for user involvement? And if it is okay, if it's acceptable to ask for user involvement, then I think it's runtime permissions would be the more appropriate, because it will give more context to the user. But if it's not acceptable to break the user's workflow and ask a question at the time of use, then it's better to fall back to this install time permission granting. So what they did in this paper is they analyzed a large number of permissions, and they concluded that most of the permissions, like 60–70%, I don't remember the exact number, actually falls into this previous category. So you can actually handle them without asking anything from the user. And only about 10 or 15% each are such that you have to resort to asking the user. So that would be one way to sort of middle ground between these two extremes that are currently being used. So the permission granting summary, I would say that first of all, since all of the mobile platform security architectures are based on permissions, granting permissions is an essential part. So unless we sort of completely revamp the mobile platform security architecture, we are stuck with figuring out how to grant permissions to applications. The current methods, so the Android prompt now is a lot better than what it used to be 2 years ago, but it's still an area ripe for research. So I have about 10 minutes, so I want to quickly tell you about what's different about mobile security, and then maybe I'll sort of end with something maybe a bit more positive than what we have been discussing so far. So usable security by itself is different, but I think what makes it more difficult in the case of mobile devices is that a mobile device is, even though they try to be like a PC, they are not a smaller version of your PC. So they have a number of limitations, right? So first of all, you are necessarily limited by the size of the display that you're dealing with. And this is not something that's going to change with technological improvement, right? In fact, technological improvement might actually work in the other way, that when I got this new laptop, it has much higher resolution, that I can't actually read the font anymore, that I have to reduce the resolution to be able to read. So this is what this means is that there is actually not enough room for all kinds of security indicators. So browsers, for example, on PCs have now gotten to the point where they're actually good at showing you indicators about sort of which URLs you are going to. So there are extended validation and lock icons and so on. And you don't have that kind of luxury on a mobile device. You are limited to a small real estate area, and like we discussed earlier, there is no possibility of reserving something like a browser Chrome, which the browser applications can't write to, but it's limited to showing trusted UI. Those are luxuries in the mobile device. So you have to come up with schemes that take this limitation into account. The input devices are also different, right? So anyone who has tried to type using a on-screen keypad knows the difference between using a keyboard and on-screen keypad. But there are a number of other differences as well. Limited battery life. The mobile device, because it's mobile, is more prone to theft and loss, and it potentially might have not as good network connectivity. And even though computational power is increasing, there is always an imbalance between what your mobile device can do and what your desktop can do. So I want to sort of stop with a few other problems that are still in this range between this tension between usability and security. So the first one is what you might call local user authentication. So this is sometimes known as device lock or idle screen lock, right? So if you mobile devices are personal and portable, and you might lose it, it might be easily stolen, and if you want to protect the information on it, you may have to have some kind of way to authenticate the user. And then today's alternatives are something like this, right? You type in a PIN code or maybe draw a PIN code, and these are really problematic. So one needs alternatives that are faster and more enjoyable and easier to use, and then maybe also more secure. The cost of not having this is really surprising. So in my case, a big multinational company wanted to have their employees read their corporate email on their devices. So they allowed people to install an application that would have access to the corporate email server. But once they did that, they wanted to make sure that because it's corporate email, you have to, they provisioned a policy that says you have to now have device lock code, so that your device would lock after 2 minutes of inactivity. And it turned out that after deploying this for a week, people actually uninstall this application rather than conform to that policy, because the policy is, of course, not negotiable because it's corporate information. So if you want to read email, even though reading email on their devices might bring them more convenience because they don't have to be in office all the time, they would actually rather uninstall the application than put up with this the hassle of typing in a PIN every time. And if you live in the north like I do, you don't want to type in a PIN when it's -25 outside or when you wake up in the morning. So the real cost was that they were not worried about this, but the company wanted the employees to read mail during evenings and weekends, and when they saw this pushback, they wanted a better way to do this kind of user authentication. So this is something that currently doesn't really have any good solutions. So there are, of course, all kinds of alternatives that are proposed, maybe something like drawing a secret, systems that rely not on you remembering a password, but you recognizing based on the idea that people might have trouble remembering things, but recall is easier, that if I show you a picture, then you will recognize that as your secret picture. So there are mechanisms that try to use this. There is, of course, biometrics and wearables, so you can have a smart watch that will unlock your device whenever it's nearby. All of these are such that that currently they are not good enough as sort of large-scale, widely deployable solutions. And there is actually a classic paper from last year, I think, from Oakland, where we tried to look at all the alternatives to passwords along different dimensions and concluded that even though along some dimensions those individual solutions are better, overall passwords still win out. But the problems with passwords, I mean, you heard this from Stephen's talk as well, that it's undeniable. So this is still something that's crying out for a better solution. And some of these might be kind of very seductive, like, for example, biometrics. But hitting the right cost and security balance is hard. And I want to sort of show you this another cautionary tale. So a couple of years ago, Google introduced this face unlock, where you can unlock your phone by just holding it against you and using the front camera to catch your face. And about a week before they were releasing this, somebody tweeted to Tim Bray, who's a well-known, he's no longer with Google, but he's a well-known Google developer, wouldn't this be easy to unlock it by just showing a photo? And Tim didn't agree to that, but that's exactly what happened a week later, that somebody showed a video where you can do face unlock by showing another phone with the photo. And it's not to say that face recognition cannot be improved, but improving face recognition at this cost point where it's just an application or at this in an ordinary mobile device is maybe not at the right point yet. So the kind of security that you can get at the cost level that's affordable is not, maybe it's good enough against your, stopping your small kids or younger siblings from reading accessing your device, but it's not enough to stop anybody else. Okay, so the couple of other problems that remain to be seen. So one is CAPTCHA. So CAPTCHA is this thing that I'm sure all of you are familiar with, that if you want to go to a web service, sometimes the web service thinks that you might not be human, you might be a software robot, and it tries to check if you're a human, and it tries to do that by asking you to read things like this. And this is an arms race, right? So I fail this half the time now because it gets more and more sophisticated, and even on a big display, I cannot really read this. And a mobile display, I simply don't have any chance of succeeding. On the other hand, this is a real problem. And I was told that if you have a web service, and this was in the context of this, the old Nokia web service called Ovi, 15% of the users for whom you show a CAPTCHA will drop out. So that means 15% of user base. And in this day where the value of your company is measured by how many active users you have, chasing away 15% of the users is not a good thing. So this is why it would be good to have an alternative. And if you don't have something like this, then there is like widespread abuse. People would create accounts and try to use them for spam or whatever. And you might argue that CAPTCHA is the wrong solution anyway, because there are systems like this Antigate, which doesn't try to guess CAPTCHA. So Antigate is a very nice service where you can give it a CAPTCHA, and it will use people in, I don't know, Pakistan or India or wherever, you can solve this CAPTCHA in real time, and it will actually quote you prices, like it will say 0.001324 second dollars for solving this CAPTCHA. Right, but barring that, there are still issues about. So the problem is, how do you know that you are being connected to from a genuine device or genuine application or something that's not a robot? And either you can have alternatives, or you can try to come up with better CAPTCHA variants. So this is an open issue as well. Okay, so I essentially in all of these cases, I effectively told you that these are problems that haven't been solved. And so what I want to leave you with is that it may not be all doom and gloom, and there might be some promising or redeeming features. So mobile devices, in addition to all these limitations, like they are small and they might be prone to theft and loss and so on, but they also have things like they have all kinds of sensors, location, motion, light and sound, acceleration. There's a rich variety of sensors, and all of this can be used to essentially get some better understanding about the user and try to set policies that might without troubling the user too much. And so I don't have time to go through this. If you look at the slides, there are some examples of how this can be done. And again, this is not without problems. So when you are collecting information about the user, and even if you collect this information only on a device and never send it anywhere else, the fact that you are collecting the information and storing it somewhere in some form and making conclusions could open to potential risks that somebody else might want to get that information as well. So we have a line of activity which we call contextual security, where the idea is that you make use of this information that your mobile device has about your activities and your movements and your interactions, and then can use this to solve problems. Like, for example, this device lock problem that we saw earlier. Rather than locking your device every 30 minutes or every 10 seconds or whatever it is, it can be more intelligent and say, if you are at home, maybe we don't need to lock it so quickly because you are at home. If you are at a bus stop, we should probably lock it quickly and then ask you for a passcode if you want to unlock it. So this kind of things might be possible, and that could be a kind of redeeming feature. So I'm not going to go through this. I'm going to just put up this summary. So I think the first point I want to make is that this is a difficult problem, but this is also a problem where you don't have the luxury of ignoring this. This is somehow has to be addressed. And bringing usability isn't just an issue of improving the UI. So you can't sort of delegate it to let the usability people handle that. It might actually mean that improving usability requires rethinking the protocols, rethinking the underlying architectures, which means that cryptographers and usability people and psychologists have to actually work together to be able to improve usability. And there are many problems where there are no real satisfactory solutions. So that's where I will stop, and I can take a couple of questions.